Good morning, energy conversion conservation class. I'm finally getting around to doing this video on the solution to the pump problems I sent out. I would really hope that you would study this and go through it. Some of these exercises are not terribly well defined, and so to keep down the amount of frustration, I figured I would just go ahead and describe my solution to you, and then hopefully you will work through this on your own to make sure that you understand these problems. They actually are pretty good. Okay, so problem number one, we have some nameplate and measured data, and we have a diagram of the system that it goes to. So we have a suction tank with some elevation of fluid in it. Let me throw my arrow here all the time. There we go. And I will be given information about this. Then we have what'll be a sharp-edged inlet, and looks like no other fittings directly into the suction of the pump. On the discharge, we have a check valve, and then we have a pressure gauge downstream of the check valve. Okay, so nameplate stuff, 100 horsepower motor, rated speed when the motor is putting out 100 horsepower is 1780 RPM. The nameplate nominal efficiency at full load would be 94.5%. Full load amps are listed at 118, and all this rating goes on at 460 volts. It's an in-suction ANSI pump. That's a pull down from PSAT, and the suction pipe through here is 10 inches, and the discharge pipe on this side is 8 inches. Basically, that's what that's telling you. Okay, on the suction side, the elevation of fluid in the tank is 15%. I'm sorry, 15 feet. Goodness gracious. I mentioned the sharp-edged orifice. Entrance to the 10-inch pump suction pipe. No other noteworthy losses on the suction side. On the discharge side, we have a 8-inch discharge check valve, followed by the discharge pressure gauge at an elevation of 5 feet, reading 53 psig. So we have the electrical data, the measured current and voltage on all three phases would be 109 amps on phase A, 107 on phase B, and 107 on phase C. And then the phase-to-phase voltages, 472 A to B, 470 B to C, and 468 C to A. Okay, and so we have three different things we're asked to do here. We want to estimate the flow rate based on head calculated with PSAT, assuming the pump operates on the manufacturer's head curve. And we'll have some curves provided to us here. That's part of the homework assignment. After we do that, we want to estimate the flow rate based on shaft power calculated with PSAT, assuming that the pump operates on the manufacturer's power curve. So that's a different curve. We get a calculated power, and we can use that to project the flow rate. And then for the third part, we're told that the actual measured flow was 2000, so which may turn out to be different than what we get in 1 and 2. So using the 2000 GPM and the other data above, use PSAT to estimate the actual efficiency and compare it to the manufacturer's efficiency curve. Okay, so that's a fair amount of stuff to do. So, you know, we have a couple fittings here, right? We have a sharp-edged entrance over here, and we have a check valve over here. So this was some of the, I think that's just cut and pasted out of the pump presentation. But anyway, so I've circled a couple of them. So for the square-edged inlet from the tank, we're going to use 0.5 as the component loss coefficient. And for the check valve, 2 is a pretty common number. So we're going to plug both of those in. Now, this is the pump head calculator from PSAT for this geometry where we have the suction tank and an elevation and all that good stuff. So, you know, you start plugging in this stuff. So suction diameter is 10 inches, discharge diameter is 8 inches. That's well and good. The suction gas overpressure, nothing was given, so we assume the tank is open to atmosphere. So there is no gas overpressure. We just have atmospheric pressure sitting on top of the liquid surface. So that's 0 psig. The discharge gauge pressure was 53. I think that was given. The suction tank fluid surface elevation was given as 15 feet. And the discharge gauge was given as 5 feet. Okay, so we're going to plug that in. Our suction line loss coefficient was 0.5. That's for the sharp edge entrance over here at the tank where the 10-inch pipe connects. And then the discharge coefficient was for the check valve right here, and that was 2. It's standard water, so the fluid specific gravity is 1, but we really don't know a flow rate. And so you can't calculate a pump head without a flow rate. And so we have a little bit of a conundrum here, I guess. So what you do is you just guess. And, you know, we were told the measured flow rate was 2,000. Of course, you might not know that on the front end, but, you know, you just got to start guessing someplace. And then we do have a pump curve. So I just said, what the heck, I'm going to throw 1,500 in here. And then this, the calculator calculates the pump head at just a little over 117. Okay, so remember that 1,500 GPM, 117 feet. Okay, so then we go to, this is the pump curve, the head capacity curve. I mean, it doesn't look like the one published by the manufacturer, but anyway, it's a pump curve. And of course, we're not showing it all the way through 0 on the feet of head axis, just to blow it up a little bit. But so we put in 1,500 at about 117 feet, and we look and we go, oh my, that's nowhere close to the pump curve. Well, so what that tells me is my initial guess of 1,500 GPM, assume, and for this part, A1, whatever, we're assuming that the pump operates on the pump curve. So we have to go back. Okay, so let's guess 1,800, you know, just how many times you have to do this is dependent upon how good a guesser you are. But I figured I'd go ahead and run a few of these out just so you kind of see it. And it's not much of a problem once you have everything set up in PSAT, or you could do this in Measure as well. And so at 1,800, we're up to 119. So then we go back, and here's my dot at, whoops, I got my dot on the wrong spot, didn't I? Dadgummit. Anyway, it should be over here. I've got it over here, but here, I'm going to fix that right now. Dadgummit. I try to do this stuff so carefully. So, yeah, that's not. There. Now, like I said, there's 1,800 and about 119 feet. Either way, it's not on the pump curve yet. Now, it's better than we were. It's better than here. Because see, this thing is going up just a little bit, but mostly it's going sideways, you know. But anyway, okay, so that's my 1,800. And so I said, well, let's go to 2,000. And so 2,000, let's see, I think I gotta turn my marker back on again. So at 2,000 GPM, I'm 120.6 feet. Okay, so back to the curve. There's 2,000, a little over that. So I'm getting closer, you know. Basically, I'm going up slowly, but basically I'm just walking across. All right, so took another 200 GPM increase here, and that gets me a little over 122. So at 2,200, I'm there. I'll start getting pretty close now. Okay. And so 2270 gets me about 123 feet. And bingo, that's on the curve. So let me see, I didn't draw arrows. I could have drawn, probably should have drawn arrows on this. I did on some of them. So this fits the scenario and puts me dead on the pump curve. So my estimate for the first part of this is that the pump curve would predict 2270 GPM. Okay. Let's see. And so that's where I have one down here. This is, I copied and pasted some of this, just wrote in some of the information. Because we're going to go to PSAT in just a second here. So you do need to average the currents. And so you add all these together, divide by 3, you get 107.67. And the voltage averages to 470. Okay, so there's 1. Okay, so then 2 says estimate the flow based on the shaft power calculated in PSAT, assuming the pump operates on the manufacturer's curve. Okay, so this condition A is what I'm looking at over here. This is garbage in condition B, so don't look at that. But anyway, I think I've put in the pump and fluid information correctly. In suction ANSI API pump. This is the pump data 1180. I'm sorry, 1780. Brain's not working. It's direct drive. We don't know anything about a belt drive. Units, standard water, 1 stage. Yes, for the optimal. We're going to stay within the same type of pump. Frequency 60 hertz, 100 horse, 1780 RPM. We specify, so you click do the pull down box and click specify the efficiency, and 94.5. We put in 460 on the volts. I didn't estimate because we were given a full load amps of 118, and we didn't say anything about a service factor. I don't think that's going to change anything. So I put in 0. If it operates all the time, I think that was information, at 5 cent electricity will give us a cost. Here's my flow rate now, 2270 from the pump curve, and it's 122.93, but PSAT rounds it, so it displays 123. My average motor amps and my average voltage here. And so this is my existing operation. I can see my pump's operating at 76% efficiency. The optimal, the Hydraulic Institute algorithms, can see 87.5, but that's kind of neither here nor there, unless we decide to replace the pump, in which case then that, we ought to be able to find something about this good. But at any rate, for this part, we're looking for the shaft power on the pump. So I've got 92.7 horsepower is what PSAT is estimating is coming out of the motor going into the pump. Okay, and so this is the power capacity curve. So I've got shaft power over here. And so what was that number? 92.7. So there's 90, 92, 94, so someplace in there, however you want to draw it, over, put a dot, and then down. And so this would predict a flow a little over 2200. I think I have done this once before, and I think I got 2230 that time. Someplace probably 2210 to 2220. Probably 2210 is probably better based on this, looking at this curve, but at any rate. So let's see, I guess we need to go back then. So however you read that, 2210 to 2230, something like that, at this horsepower. But that's how you do number 2. And then number 3, we want to put in the actual flow rate of 2000 GPM and the other data that we need, the pipe sizes and all that. Use PSAT to estimate the actual efficiency and compare it to the manufacturer's efficiency. And let's go back. I think I ran whoops, 22. Here's 2000. So my feet ahead at 2000 GPM is about 121 or 120.6, something like that. So yeah, okay. So let's see, where did I do this one? I'm still in condition A over here. I could have left A alone and done this in B, but anyway, because this is even weird units. So this B doesn't have anything to do with this problem. Okay, so I think most of this stuff is the same. We changed the flow rate and changed the head, kept the electrical power because, you know, we really didn't change where the pump was operating. We just changed our methods for estimating the flow. And so if this is if we had a flow meter and then when we went through the head calculation, we would have got a little less than 121 feet. We put that in with our measured electrical. And now we get a pretty good efficiency. I'm not saying it's a good number, but and I think our calculation's pretty good. So we get 65.7%. Well, we still say optimal would be 87 under this condition. So it looks like maybe we're not doing so good here. The optimization rating is about 75.5% on this guy. Okay, and that's this. That's the brake horsepower. That's the motor output power. 70 divided by 92.7 should be 70.5 roughly. Okay, so when I take 2000 and this is my efficiency versus flow rate curve, and I go up and over, oh my God, well, I've got 78% coming off of here. So this pump was never as good as the estimates from the Hydraulic Institute. Okay, that's pump 2, so we go back to, okay, so this is where I wrote the numbers down. So we're 2000 GPM at 121 feet of head. Manufacturer's efficiency is 78, and the PSAT efficiency is 65.7. So looks like we're degraded. It could be some issues with the impeller. Something's not quite right. Wear rings could have opened up. We may have some leakage, recirculation, whatever, but it would be cause to maybe open this pump up next time we had an opportunity and take a look at it, see if we can figure out exactly what's wrong with it. Okay, so that's number 1. Okay, so number 2, whole nother scenario. Do a PSAT analysis of this pumping application. So we got a suction tank. This time we're pumping to a discharge tank up on the hill. We got elevations. So the free surface in the suction tank is 10 feet, and going up the hill, this free surface is 120 feet. So the difference in free surfaces is what, 110 feet. And I don't think, we don't have any gas overpressure, so your static head on this is going to be 110 feet. Okay, so motor, again, 100 horse, 1780 RPM, 118. So yes, looks like it's the same motor that we had before. This time we have 4-cent electricity, operates all the time. Again, it's an in-suction ANSI pump, 1 stage, and we're pumping regular water. Here's our amp measurements are a little bit different here, not a lot, 105, 106, 110, and we're just given the average voltage at 472. We're given the flow rate, 1500 GPM. Okay, so we look over here at the diagram. So we got a discharge gauge on the pump at P1. We've got a check valve, and we've got a P2 that's measured just on the downstream side of the check valve. All the gauges are 5 feet elevation. In pipe diameters, I got 12 on the suction and 10 on the discharge. And all this stuff is at 10 inches on the discharge side of the pump. There's our flow meter. There we go. Okay. So, well, we're going to have to do a PSAT analysis. So we know we're going to have to calculate pump head. Let's see. So we just plug everything into the diagram that shows the suction tank. So 12-inch pipe on the suction, 10 on the discharge. Let's see, I think we had, yeah, we had 80 PSI. I'm distracted here for some reason. On the discharge, 0 up here. That's the gas overpressure. We don't have any. 10 feet on the elevation here and 5 feet on the gauge. And discharge coefficient, it's the sharp-edged entrance on this side, and if you, like, there's nothing between the pump discharge flange and the pressure gauge. So we don't have any loss in there, nothing significant enough to include. Specific gravity 1, and our flow rate is 1500 GPM. So pretty simple. Plug it into the head calculator, and bingo, you can look at all of these. But 180.59 feet, okay, at 1500. Okay, so let's go over to, we call it PSAT, start putting in our numbers. All this stuff pretty much the same. Didn't change anything here. 1780, all this was the same. Operating fraction all the time, 1 at 4 cent power, 1500 GPM at 180.59. PSAT rounds it to 181. Motor amps average 107, and the voltage is 472. Okay. So this is what's going on the existing pump. Okay, so we've done the PSAT analysis. Now let's go see. Okay, so I think the first thing we just said is, well, do a PSAT analysis. So, okay, so we've done that. I didn't really ask any questions about it. Then it says calculate the loss coefficient K for the check valve. Okay, so there's two ways we can do this with a hand calculation, because we have a delta P. It's what it's losing 4/10 of a PSIG. And so we've got a simple equation for that, or we can use the valve tool, which is what I've done because I'm lazy. Once you get used to using these things, they're so nice and quick, and they do a really good job. So anyway, if you call up valve tool, when you download PSAT, it comes in the same directory. It shows up in the PSAT directory. So you pull down your units and establish these. You figure out what we've got 4 inputs. We've got upstream pressure, we got a CV on the valve, we got downstream pressure, and we got flow rate. So those are the 4. So you have to know 3, and then, so you just do the pull down menu to figure out what you want to calculate, assuming that you know the other 3. Well, so we don't know the CV on the valve, but we know everything else. So we put all that stuff in. And we've stuffed in, this is operating fraction and the electrical cost, and these are just some nominal values for pump efficiency. I mean, we could go put in better values, but we're not really using this right now to look at the cost of the friction. So what we're really doing is wanting this to calculate the CV for the valve. So in that case, it doesn't matter what you put in here, but those are, probably a little high on pump efficiency, but motor efficiency is about right. Okay, so I plug all this stuff in. Upstream pressure 80, downstream 79.6. Everything is 10 inch. The gauges are at the same elevation, so that'll cancel out. My flow rate, specific gravity, and bingo. It gives me the K value And say it knows there's no reducers or expanders because I got 10 inch, 10 inch, and 10 inch. So those get zeroed out. And so I have the K for the valve, which is the total K from this pressure to this pressure. Okay, so 1.58 is my answer. Or I can, it's pretty trivial, the calculation, but this is the valve uh, equation. Flow is CV times the square root of delta P in PSI divided by specific gravity. And notice there is a geometry in F sub P factor, but when everything's the same diameter, the geometry factor is 1. And so you just do the math, and guess what? You get the same value. So, okay. Now life gets a little more interesting here. And this is where I really need to rewrite some of this because this thing gets a little bit confusing at this point. So we're going to change the fluid. Everything's going to stay the same, except the fluid is going to change. But however, some of these measured quantities would change. And see, that's what I need to be a little clearer on. But so you repeat the analysis in terms of the elevation and the pipe size, the check valve, but the pressures we're going to see are going to change. The flow rate we're going to keep to be the same. The elevation and all that stuff are going to be the same. So when you change it, you note that the specific gravity is 0.82 and the viscosity is 2.7 centistokes. So the viscosity is 2.7 times what it was before, and the specific gravity is what been reduced by 18% from 1 to 0.82. And so the question is, what impact is this going to have on the pump? Well, this is some stuff we really haven't talked about. And so this is a good opportunity. So, you know, if you go out and search the literature and look around a little bit, you can find, and I have not mentioned this yet, but pump head developed by a centrifugal pump is independent. This is the head or the discharge head, the pump head, what the pump, the pressure increase that the pump puts into the fluid. The pump head is independent of the fluid pump so long as the viscosity is relatively close to that of water. And of course, then the question becomes, what is relatively close? And I've got a rule of thumb of about a factor of 4 before you really have to get a separate pump curve. Now, if you have enough of a viscosity increase that you're concerned with it, you have to go back to the pump manufacturer, or it could be some these days on some of the pump selection software online that you can put in a viscosity, and it will, based on the manufacturer's information, modify the pump curve. But all standard pump curves are put out for standard water. And so when you start pumping something else, you have to be concerned that that curve is still going to work for you. Okay. So in this case, the viscosity increase is not enough to significantly alter the pump performance curve. So that means that the pump head will remain at 180.59 feet. And in order for that to occur, the discharge pressure has to drop, as we'll see when we go to the pump head calculator. So changing the fluid to kerosene will only change the pumping power and the discharge pressure. So the reduction in density will drop the pump power because you're not pushing as much mass, because you maintain the same volume flow, but it doesn't weigh as much, and so it doesn't require as much power into the pump. So our point of operation on the pump curve will remain the same. So I think it turns out we were 74% before. So then we will still be at 74%. And what you do is you adjust the amps on the PSAT analysis for the kerosene in order to have a 74% pump efficiency, again, as we'll see. Okay, so here is the pump head calculation, and now when we put in this reduced specific gravity, then the pump discharge pressure changes in order to give the same head. If I leave the same discharge pressure, this head goes to like 221 or something. And we know from pump theory that that's not going to happen, that this is going to stay the same. So what you have to do is monkey with this, reduce this pressure until you get 180.59 again. So it's about 65.6 PSIG. Will do that for you. And so that way we maintain the same pump head. Okay, so condition A in this PSAT analysis is water, condition B is kerosene. And so I basically just hit the copy A to B button and put all the water stuff over here and then change the stuff that I needed to. So we changed the kinematic viscosity to 2.7 centistokes. We changed the specific gravity to 0.82. The rest of this didn't change. It's the same pump. Operating cost didn't change. Stand 1,500 gallons. It's the same pump head. But the voltage, I didn't change. The voltage not going to change much. But so what you have to do then is you have to adjust these amps to give you 74% pump efficiency, because we're operating at the same point on the pump head. Now there is one thing I guess could happen here, that the motor actually could speed up a little, because the motor power is going to drop from 92.4 to 75.7. That's pretty far down in the weeds. You could project that a little bit, and then you would have to plot up the pump curve, system curve, and see that might give you a very small increase in fluid flow. But within the basic assumptions of using this given data, I wouldn't expect anybody. I didn't go to the trouble to do that. I wouldn't expect you to either. Okay. So, I mean, it is interesting. If this pump is pumping 1,500 GPM of water, it's going to cost $25,500 a year. If we change it to kerosene, it's only going to cost $20,900. Kind of by the by. The optimal efficiency doesn't change on either analysis. Okay, so let's see. That's just kind of repeated the assignment. I'm just noting here that the static head is, 120 minus 10, which we already talked about. And so then the first point it asks is, what is the system frictional head with water? And well, it's the total head, 180.59 or 0.6 is equal to 110 plus the frictional head. And so you can just subtract 110 from this, and you get 70.6 feet of frictional head at that flow rate. If the fluid was switched from water to kerosene, but no other changes were made, and see, that's what's a little misleading. Some of the stuff changes, like the power changes and, that sort of thing. And the pump head stays the same, but the discharge pressure changes. And so, if you're not fairly experienced with this, when you read that, you're not sure what to change and what not to change. Flow rate does not change. Viscosity change is too small. Head is independent of the fluid. The pressures do change. Discharge pressure is 65.6 PSIG instead of 80. If so, why and in what direction? Well, I think we've already answered that. And similarly, would you expect motor current to change? And yes, because the specific gravity says this kerosene is lighter And so it's roughly 82% of that of water, and we already talked about the actual numbers right here. Okay, so problem 3. We have, again, a suction tank, sharp-edged orifice. We have just a straight pipe into the suction gauge. Then we have the discharge on the pump. We have a check valve, and then we have the discharge gauge. So the flow rate here is 2,000 GPM. We got standard water, specific gravity 1. We've got suction and discharge diameters, suction 10, discharge 8. Pressure, suction 8, discharge 115, and elevation 4 and 6. Okay, so we want to estimate the pump head, and so we'll have to estimate the manufacturer's loss characteristic on the check valve, which is in the next page. And then we want to estimate the level in the tank, assuming a sharp edge entrance, orifice at the entrance with a K of 0.5 and 5 feet of pipe between the tank and the pump suction. Okay, so we're at 2,000, and these are the curves that came from the check valve manufacturer. And so this one predicts for the given size, and we have an 8-inch check valve. So at 2,000, we read up and over, and that says we're going to have 4 feet of loss. So this doesn't give us a K, this gives us a actual feet of loss across the valve. So we have to play with this a little bit differently. So what you can do is you can go and you can calculate the K based on that 2-foot loss flow rate, or you can just put all the information into the head calculator, and you can monkey with this discharge coefficient until it gives a 4-foot frictional head loss on the discharge side of the pipe. So either way, this is, I think we actually for a different situation, we actually calculated this same K before. But at any rate, so I've got 10 inches and 8 inches. I've got 8 PSIG, 115. I've got 4 foot and 6 foot. And on this one, I don't have any fittings between the gauge and the pump. And so I put in 0 here, the 1.58, the 2,000. And I get, it's about 255 feet ahead, 254.75 is my feet of head, okay? So let's see, what was the first thing? So estimate the pump head, okay. So that's the pump head. Now we want to estimate the level in the tank. Okay, so we keep all this information the same, and basically what you do then is you change this tank level from this picture in order to have basically the same pump head. So it's pretty close. I think it's 254.75 is 254.79. I mean, you could shave a little off of this. But basically, so this elevation is 24 feet in the suction tank. So that's pretty cool. Okay, and that just shows the information written in. Okay, so problem number 4. So this is a vertical turbine pump, and so the impeller stages are down here, well below, submerged below the level, the water level in this well. Sometimes these are called wells. So we got 1, 2, 3, 4. It's actually a 5-stage vertical turbine pump. Motor sits up here. It's just on a long shaft. the inlet. This is just kind of, I don't know, this is the inlet to the pump, and the first stage starts right here. So that's in terms of elevation of fluid above it, that's the elevation that we're wanting to take into consideration. Okay, so condition A, we have one 300 horsepower, 1770 RPM motor with a vertical turbine pump operating. Pressure was measured in the discharge header, operates this condition 40% of the time. Okay, so this is the water fluid is treated water in a water treatment plant, 6 cent power. So we pump, so the impellers push up through here. And what do we got? We've got a hydraulically operated full port ball valve, 10 inches. We got a 10-inch gate valve. And we've got, then we go from 10 to a 20-inch pipe. And there we go. So, okay, so I look at my gate valve in the fully open condition, it's 0.2, and the ball valve is 0.1. And the pump head, well, just a second, I'm going to pause for just a second here. Okay, so here we are calculating the pump head for the case of 2000 GPM. And like we had said previously, these are the circuit values are taken as the loss coefficient for the gate valve full open. Use 0.2 for the ball valve full open, use 0.1. And you do need to note that if we look at the diagram here, this pressure is measured in a 20-inch pipe, and these are 10-inch gate valves, gate valve and ball valve. So there's a little note down here, and if you read this, what it says is that if the fittings are of a different diameter than the point of pressure measurement, that you have to adjust the K values. And so you take the ratio of the diameters. It does a little example here where the pressure measurement's a 12-inch versus a 6. Well, we're a 20 versus a 10. The ratio is the same. You take it to the fourth power, which is 16, and then you multiply it by the what you have looked up for your K values, which is 0.1 plus 0.2 is 0.3. So 0.3 times 16 is 4.8. And so that gets inserted here as the discharge line loss coefficients, the sum of them for those two valves right here. It doesn't make a whole lot of difference in this case. It changes it a very small amount. But at any rate, so having done that, with the rest of the information put in, we get a pump head of 265.57. And so let me see. And then we have another condition here, condition B. We're at 5,000 GPM, and we have a higher power, obviously, on the pump. And obviously, and also, well, not obviously, but in condition 2, we're going to operate 3 of these pumps in parallel, and they're all the same pump. So 3 in parallel, all 300 horsepower. So we're running 900 horsepower worth of pumps, 1770 RPM motors, and they go into a distribution header, and this is where we're measuring the pressure is in that header. And it operates in this condition 30% of the time. Okay, and the power goes to 154.2 kW. I'm sorry, the pressure and the power. We had 170 before with a 1 pump. With these 3 in operation, we have 165, 165, and 160. So we'll have to sum that. So we'll run one big equivalent pump in PSAT. Okay, so this is the head calculation at that point. I think the only thing that's really changed here is the discharge pressure and the flow. And so we're about 166.7 feet, something like that. Okay, then to calculate system curves, and I think we're asked to do this with two different exponents. We're asked to do it with an exponent of 1.9, and then the next slide is doing it with an exponent of 2, just to see the difference. So we had 2,000 GPM at 265.6 feet of head and 5,000 GPM at 366.7 feet of head. Okay, and so that's the fluid horsepower by the by. But here's the static head calculation, and this is the K prime loss coefficient that goes into this equation right here. So the static head is 244.1, and this K prime is 1.14943 exponential minus 5. Okay. So that's with the exponent of 1.9. And then we go with an exponent of 2. We still have the same operating points. We put that in. And now the static head comes up 246.3. And the K prime loss coefficient is 4.81464 times 10 to the minus 6. So those are those two equations. And so this is just kind of given the information that's asked. One was just the pump heads. So we've already talked about that. And 2 is the equations. We just looked at it, just puts it in equation form for you. What is your estimate of system static head? So we see with 1.9 it's 244.1, with 2 it's 246.3, so not much difference on a system this size. And then if you exercise these equations with 4,000 GPM, you'll see that with the exponent of 1.9, the total head is estimated at 324.3, and with an exponent of 2, it's 323.6. So for all practical purposes, it's about the same thing. Full load amps, it says that the motor nameplates were missing. And so, you know, that's one thing that you can do in PSAT pretty easily is estimate full load amps, standard efficiency, 300 horsepower, 460 volts. It's 339.8. I've got the PSAT analysis come up here in a second. And then the optimization rating for condition A, which is at the 2,000 GPM, that pumping operation is 68.9% of the optimal. And at condition B, we're 81.3. Okay. And so this is the PSAT analysis. All the data put in. This is where you just estimate full load amps. There's the 339.8 in this condition. There's the optimization ratings. There's operating cost. This is, we spend 40% of the time at 2,000 and 30% of the time at 5,000. So you can see the relative amount. So this is so well over $100,000 between these two conditions. That's just for 70% of the year. Okay, so problem 5. So what we're going to do here is the pump curves for the pumps used in exercise 4 are in the exercise 5 data.xl file, which I will send out to you. Well, it's not located on your flash drive, but I'll send it out. Calculate the pump efficiency for all flow points in the table for a single pump. Fill in the columns for the composite 3 pump performance. Plot the pump head curves, preferably in Excel, which is what we've done. Using the system curve you generated in example 4, and I used the one for exponent 1.9. Export the coefficients to spreadsheet, then copy these coefficients, paste them into the cells, etc. Add the system curve to the pump head curves, and are the pumps performing according to the manufacturer curves? If not, what are some possible reasons? So we got to do all that. Okay, well, this is the calculated. This is what you should get on the calculated efficiency. You're given the first 3 columns, and so the efficiency is the brake horsepower divided into the water horsepower, and the water horsepower is GPM, feet of head, divided by 3960. Okay, and so it's pretty simple. For example, on the 500 GPM point, if I take 500 and times the feet of head times 493 divided by 3960, that's 62.25. And if I divide that by the brake horsepower divided by 127, I get the efficiency. Okay, and etc. So you go down through here and calculate your pumping efficiency. Okay, I may have misspoken a second ago, so let me go through that again. Let's calculate this 41.8% efficiency. So 500 times 493 divided by 3960, and then divide that by 149, because that previous calculation is the water horsepower. This is the brake horsepower, and that ratio is the pump efficiency, and it comes out. When I punched it a second ago, I punched the 127. It didn't come out, and I about had a heart attack. Anyway, they're correct. And then you do for the efficiency, you do the same thing for the 3 pumps. This would be with 3 pumps operating. These are the operating points, and this is the brake horsepower. So you do the same thing. So that's pretty simple. And I'll show you the Excel sheet here in just a second. But when you, so this is the single curve. And so you take each one of these flows and you triple it, and then you plot the 3 pumps in parallel curve, and then you put your system curve on it. And so our operating points based on the analysis would be here for 1 and here for 3. Well, at 5,000 C, and then these are the actual, this is the system curve, and these are the measured or the desired, I guess measured or desired flow rates, 2,000 and 5,000. And you see, if we were on the pump curve, it says this pump would be producing significantly more head. So it doesn't look quite right. And then if you take this operating point, then each of the individual pumps would be back here, which you see that's not on the pump curve. So it's starting to look like these pumps may be degrading a little bit. Okay, when I check efficiency, this is just a plot of the efficiency versus flow for the 1 pump and then for the 3 pumps. And then these are my operating points, and you can see I'm not quite up to snuff. I mean, 3 is doing better, so it could be just one of these pumps is degraded. But it probably would require some investigation. And then here is the flow versus power curve, and you can see we're not using quite the power that would be projected, which would be an indication that maybe impellers are damaged or clearances have opened up. Okay, so that's the end of the PowerPoint file. And then let me throw up the Excel file here. Well, let me see. I think I have shut it down. So let me go back, put this up. Exercise. There we go. There we go. Okay, so this is what a file looks like that gets exported from PSAT. You get coefficients up here. It will plot out uh, your system curve for you. I mean, you can do this for yourself just easily. And now to this has been added the single pump curve, GPM, feet of head. So this, we got the manufacturer pump curve, and we just translated these 6 or 7 points. And then to get the 3 pumps in parallel, we picked the same feet of head, but we tripled the flow rate. So it's 500 here times 3 is 1500. And then we got 493 and 493. And so each one of these head or flows is 3 times the single pump, and the heads are the same. And then you plot those up. Okay. And then I just put these operating points, plotted single points over here. So we could see that. Okay. So, we're not operating on the pump curves as would be expected. So we would expect some sort of degradation uh, in the pumps that would just have to be investigated. Okay, so I think I'm going to stop this now and post it, and we'll be back in class on Tuesday and Thursday. So I hope you guys have a great weekend.